Hey guys, this is Mr. Bennett, and this is Unit 16, video number 2. We're going to talk about something called Le Chatelier's principle, and this is going to build on what we talked about yesterday in video 2 in terms of reactions and the rates. So the first major concept that we're going to talk about here is reactions at equilibrium, and the first key idea to this is that all reactions are reversible in principle. Well, what does reversible mean? That means that they can both move in the forward direction, what we've talked about kind of all year, where you have essentially your reactants and they turn into your products, right? But it turns out that theoretically, another way of saying in principle, the products could be used, you could reverse that, and you could take the products and turn them into the reactants. Okay? So when we look at reactions as being reversible, instead of using that classic kind of like one-sided arrow, like so, we are going to use a double-sided arrow. So an arrow that goes in both directions, forwards and reverse. You could also use two arrows like so. Either one works. Okay? And it turns out that if the rate that's going forward and the rate that's going reverse are equal, meaning you're forming products as fast as you're forming reactants, then we call that dynamic chemical equilibrium. It is the state of a reversible reaction when the forward reaction rate is equal to the reverse reaction rate. And I just always remember that in equilibrium, okay, equilibrium sounds like equal. It's all about the rates being equal. And it also turns out that natural reactions will actually adjust towards equilibrium if they can. So it's kind of a natural thing for reactions to be at equilibrium. All right? And it turns out that the scientist who kind of figured this out, that reactions will adjust naturally, his name was Le Chatelier, and his principle was that when a change is imposed on a reaction at equilibrium, the forward or reverse reaction rates will shift to return to equilibrium. In other words, if we upset this reaction, if we do something to stress it out, to cause problems, then the forward or reverse reaction will speed up in order to bring it back to this natural equilibrium that all reactions are trying to get to. So what is a change? What sort of changes can we make? Well, there's three big changes that we're going to consider. So concentration, temperature, or pressure. Okay, those are the big three, and you need to know if we change the concentration, the temperature, or the pressure, you need to be able to figure out how it will shift the reaction rates. Okay, and these shifts or changes, actually the changes that we're shifting towards, are also referred to as stresses. So you could say that you're stressing a reaction and it causes a shift in the rates. What does shift mean? It just means that it's going to, if equilibrium is a balance, where forward and reverse are equal, a shift means that the forward reaction may speed up and the reverse reaction will slow down, or you could get the opposite, where the reverse reaction speeds up and the forward reaction slows down. So let's talk about what that looks like. So there are three different types of stress that we can put on a reaction. The first one we're going to talk about is concentration. In other words, we're going to change the amount of reactants or products. So in other words, we can increase them, or we can decrease them. Okay? In other words, we can add reactants or remove reactants. We can add products or remove products. So here's how I think of it. First of all, if you add a substance, it will shift the rates away from the substance. And in fact, this is my way of remembering it. Add starts with A, and we're shifting away. Okay? So in other words, if I add some A, it will shift it to the other side of the reaction. So in other words, the forward reaction is going to speed up and the reverse reaction is going to be kind of slow. Okay? In terms of what we talked about yesterday, you could think of this as particle collisions. If you have more A in there, that means more A particles are around to collide with B, which means you have more opportunities for reactions. Okay, now let's say we want to remove A. We could put remove here, but I don't like the word remove. The word that I like is to take. To take a substance out will shift the rates toward. And again, this goes back to having a trick. So I think of add away, AA, and then I think of take, the T in take, as standing for toward. So T for T. Take toward. So in other words, if I remove some A, so if I take some A out, that means there's less A particles moving around, which means less A particles will collide with B, which means less opportunities for a reaction. That means that the reverse reaction is going to be going faster than the forward reaction. Okay, so the rate will shift toward the substance we removed. Okay, so that's concentration. Now pressure is a little tricky. Okay, so let's talk about pressure. If we stress a reaction using pressure, it turns out that pressure affects the reaction rates based on the amount of gas particles. Okay, and this part's really important. It's all about the gas particles. Okay, so adding pressure, in other words, if we increase the pressure, it will shift the rates towards the side with the least number of gas particles. So let's look at this particular reaction over here. Notice we have three gases. We have gas A plus gas B will produce gas C. Okay. Now if we count these up, all of these have a coefficient of 1, so we could think of this as one A gas particle combines with one B gas particle to produce one C gas particle. So in other words, on this side we have two gas particles. On this side we only have one gas particle. What that means is by adding pressure, again, it's going to shift towards the least number of gas particles. So if we add pressure to this, the forward reaction is going to increase in its rate, and the reverse reaction is going to go very slowly because it's going to, again, shift, or the rate's going to increase to the side with the least number. Now, if we're to do the opposite, if we lower the pressure, or reduce, whatever word you want to use, if we lower the pressure, it will shift the rates towards the side with the most number of gas particles. So we already said this side had two gas particles, this side has one. So if we lower the pressure, then we're going to get a shift that will increase the reverse rate, and the forward rate will go kind of sluggishly or slow. Okay, so that's pressure. Again, it's a little tricky because it has to be a gas. Let's say you had a solid in here, you wouldn't even count the solid. So if we had something like, I don't know, letter D, but it's a solid, it would not count as a gas particle. You'd still only have one gas particle on this side. You'd totally ignore a solid or a liquid. Okay, there's another little extra thing, and that is when we're dealing with pressure, kind of put a little star here if you want. This is an extra idea. If you add an inert, or what we call noble gas, so if you add a noble gas, something like, for example, helium, okay, or neon, if you add an inert gas, it will have no effect. Okay, I know normally when we add a gas to a container, that means more collisions within the container, which means a higher pressure. But it turns out, since inert gases don't react, their collisions are not going to create any more reactions. Okay, and they're going to interfere with reactants colliding with each other, as well as products colliding with each other. So their interference in terms of the reverse and the forward reaction is the same, and they're not creating any reactions themselves. So they essentially have no effect on equilibrium. Equilibrium will stay the same. They're inert in terms of reactions, and it turns out they're inert, meaning they have no effect on equilibrium as well. Okay, so now let's talk about the third and final way to stress a reaction. That would be temperature. Temperature is actually pretty easy if you understand concentration, because it turns out that heat will act like a substance. So in other words, just like how in concentration we added a substance and it shifted away, we're going to see that same behavior when we're talking about temperature. So if we add heat, it will shift the rates away from the heat in the equation. So you can think of it over here. Here we have our equation. I've added some heat here. So if we add heat, it's going to shift it away. The heat is on the right side of the equation. So shifting away means it's going to shift it to the left, or it's going to increase the reverse rate. Think of it either way. It's shifting in a direction, so shifting left, which means the reverse rate is increasing, and the forward rate is going to be kind of sluggish, slow. Now the opposite, we added before, so now we want to do the opposite. We want to remove, but remember, I like the word take better. So if we take heat out, and another way of thinking of this is if we cool it, right? Adding would have been heating, just to think of it in terms of, right? So if we cool it, or if we take heat out, it will shift the rates toward the heat in the reaction. So in other words, if we remove some heat, it's going to increase the forward rate, okay, or it's going to shift it to the right. Okay, so just like a substance, it has the same effect in terms of the add, away, take, toward. Okay, the last little extra tidbit I want to give you, and this is kind of like that inert gas thing, okay, but yesterday we talked about different ways that you can affect the rate of a reaction, and one of the things that we talked about was a catalyst. Okay, so catalysts, it turns out, okay, have no effect on equilibrium. And I should have a little line here. So adding a catalyst has, I guess, we want proper grammar, no effect on equilibrium. Okay? Turns out that catalysts favor their forward and reverse reactions equally. Just like how those inert gases cause the same amount of interference for the first forward and reverse reactions, catalysts speed up the forward reaction as much as they speed up the reverse reaction, so the overall change is zero. Okay? So the way I want you to think of it is catalysts and inert gases, also known as noble gases, no shift. Okay, they have no shift. They don't cause any shift to the equilibrium of the reaction. Okay, so that's it as far as notes, but I want to do a little bit of practice with you just to show you how we apply this. Okay, so practice problem here. What we need to do is figure out which direction, left or right, that the equilibrium will shift. And I know there's a little typo here. Let's get rid of this word. So which direction, left or right, will the equilibrium shift if the following changes are made? And here's our reaction. Okay. So A says we're going to add nitrogen oxide. Okay. So let's find it. Be very careful here. You want to make sure you're looking at this nitrogen oxide, not the dinitrogen oxide over here. Okay. So here we have our nitrogen oxide, and we're going to add some. Okay. Now remember, it's add, away, right? So right now nitrogen is on the left side. This would be if we do a little line down the center, right? This is the left side, which means if we add nitrogen oxide, it's going to shift it away. So it's going to drive the forward reaction to occur faster, or it's going to shift to the right. Okay? Now, if we look at the other nitrogen oxide, the dinitrogen oxide on this side, again, it's saying that we're adding. So if we add dinitrogen oxide to this side, right, that means that it's again going to, if we add, we go away, but this is on the right side. So by adding dinitrogen oxide, we're going to actually shift it in the other direction. This time, the reverse reaction is going to speed up, which means that it will shift to the left. Okay, so that's adding, that's all concentration based, right? Now let's talk about pressure. Okay, I'm going to clear things up a little bit. So again, the big tricky thing about pressure is that you only care about gas particles. Okay, it's all about the gas particles. And remember, if the side that has the most, actually we'll say if we increase pressure, it's going to favor or shift to the side with the least, right? If we decrease pressure, it will favor the most. So in this case, we are increasing. So that means that we're increasing pressure. We're going to favor the side with the least gas particles. Okay, so let's count it up. If we look at this side, this hydrogen has a coefficient of 1, right? 1 hydrogen, and this nitrogen oxide has a coefficient of 2, so that means 2 nitrogen oxide particles. Put that together, that's 3, 1 plus 2, 3 gas particles on this side. Now let's look at the other side of the reaction. So on this side we have 1 water gas particle and we have 1 dinitrogen oxide gas particle. That's it. Heat doesn't count, it's not a gas. Okay? Put these two together, that means that we have 2 gas particles on this side. Okay? And again, we are increasing the pressure, so that means we're going to favor the side with the least. In other words, the reaction that creates the side with the least will be sped up or increased. So if we're favoring that side, that means this is on the right side, so therefore the forward reaction is going to increase. Okay? So it's going to shift right. It's shifting towards the side with the least number of gas particles, the side that has 2. Okay? So last example, last practice. It says the system is cooled. Okay, so what does that mean in terms of heat? If it's cooling, that means that we are decreasing heat, right? We're removing heat. Okay, you could think of it as we are taking heat out, right? We're taking heat. So taking moves toward, because remember, heat works just like a substance. So we find the heat in the reaction. In this case, the heat is on the right side, right? Because there's our arrow. Okay, and we're taking it out, which means it's going to shift toward the side with the heat on it, and so that means it's going to shift right. Okay, so make sure that you complete your whisk, and we will see you tomorrow.